So today we are going to talk about the split brain of Kubernetes and how to run our traditional workloads on Kubernetes. So who here have used Kubernetes before? Raise your hands. Awesome. Installed Kubernetes? Okay. Ran stateful applications in Kubernetes? Quite a few. Anyone wants to do the talk instead of me? There was one hand there. So today we are going to talk about stateful applications. And before that, I've seen that half of the room here have not risen his hand on saying they have experience with Kubernetes. So I'm going to do a quick overview of what Kubernetes is and like the basic constructs of Kubernetes. Then going to touch a little bit about how generally applications in Kubernetes works, the stateless ones. And then going to talk a little bit about the stateful applications, how to run stateful applications in Kubernetes, or at least the basic principles of how to build the stateful application on top of Kubernetes. And the emphasis here is on build, because again, Kubernetes is an awesome tool, but it still requires a lot of work to actually make it useful for production use cases. So just to set a little bit of context about myself, so my name is Arthur Berezin, I'm the founder of a company called Jovian-X. And basically what we do is we take applications, on-premise applications, and we turn them into SaaS-based applications. We do that by all sorts of magics in Kubernetes and basically building best practices on top of Kubernetes, running these applications and providing all sorts of services around them to make these applications SaaS ready. And obviously, as I stated, we, as most companies in the world, using Kubernetes as our basic building block on top of various public clouds in order to build these kinds of applications, right? So when you use SaaS applications today, you log into your service, you're used to having your data in there, right? I've seen a presentation today by JFrog, other fellows such as Redis and others are also using very similar best practices. But again, Kubernetes, when we think about how Kubernetes was born and what kind of workloads was intended to run, right? These are not these cases where you actually have the state stored and ready as terrible things happen to your application, right? Usually it's the stateless applications. These are the first cases where Kubernetes was used essentially to run basically Docker containers at scale and orchestrate and schedule them across multiple nodes. So let's cover like quickly the basics of Kubernetes and what it takes to run Kubernetes. So you have the principle of a Kubernetes cluster. Within a cluster, you have a master node, which basically manages and makes sure that everything that's needed to happen in the cluster actually happens. And then you have the nodes themselves that run the actual workloads. And the nodes themselves have node processes that maintain the Docker containers locally on each node. But the master is the one controlling the application. It's the component that actually makes sure that if something happens, if a container fails, it's the one responsible for rescheduling that. So as I mentioned earlier, you have the notion of a containers application, which is basically a Docker container or a set of Docker containers running within the Kubernetes node. But that's not the fundamental basic building block of Kubernetes, which is a pod. And you also have the notion of deployments. So deployments are actually managed from within the master node. The deployment is a controller that runs within the master node, and it's the one monitoring the status of the application and makes sure that it actually runs as intended. So as you've probably heard in the previous sessions today, Kubernetes basically runs based on YAML files, and you describe the intended state. And then Kubernetes actually makes sure that this is the current running state. So if you describe in the YAML file that you need 2 replicas or 5 replicas of an application, you have a controller, some sort of a controller that actually makes sure that happens, and deploying it is one of the controllers available within Kubernetes. So let's dig a little bit deeper into the node itself and see what we have inside there. So as I mentioned earlier, the basic principle, the basic building block of Kubernetes is a pod. A pod can run multiple containers. And these containers share resources between them. Now you can attach resources such as volumes to a pod, and obviously all the containers within the pod share that data, that information. Very useful for cases where you have multiple components that you need sharing data, and also you have an IP that is attached to a pod. And obviously, all the containers within that pod are available through that IP address. Now, on top of that, you have a notion that is called a service, or actually, that's the way you make your deployment available externally. So the deployment is responsible for making sure that the pods are running, and the way you expose that service externally, you make that service available externally, is by defining a service, and that service can basically specify on how this service is available, and you can use multiple cool stuff such as load balancers and other means to access the container itself. And another very important principle of Kubernetes is the ability to scale the application. Now, obviously, lots of people mention that Kubernetes have this built-in principle of high availability built in, but what this actually means is that you have to make sure that the container that you're scaling or you're building or you're running is capable of handling these workloads. Obviously, in stateful situations where, for example, you have an application that is not intended to run within a containerized application, you need to make sure that when you set up this environment, when you do a scale-up operation, these containers can actually handle that. So, as I mentioned earlier, originally Kubernetes was designed for the cows use case, a term coined by a familiar guy from the OpenStack community, saying that there's cattle and there's pets and versus cattle's use case, where you have OpenStack and virtualization management technologies are the pets, where each and every VM is a pet, but cloud and stateless applications are kind of like cattle, where you don't have a name for you don't have a specific name for them, and you just scale them infinitely. So now we're going back to the pets use case with Kubernetes as well. So it's interesting to see the containers and the Kubernetes community going back and re-implementing the same stuff we've been doing with OpenStack some time ago. So what it takes for an application to be stateful. So the first part is that there are various attributes that we need to take care of when we build an application that is stateful. We need to make sure that we have the storage available and persistent, right? We're writing to disk, writing to a file. If something terrible happens to our VM, hey, we need to make sure that this data keeps being available, and we know where it sits, and the various application files accessing that volume know always where that volume is and who that volume is. There's also the notion of identity, right? Now, in the era of cloud, we don't really care about how we name VMs, as long as they have some sort of a unique ID and they can scale automatically, et cetera, et cetera. Now, for the stateful cases, identity is really important, right? I have a name of a machine, a name of a container, and that container needs to access its storage. Now, it's a one-to-one relationship. So the name is really important, and we need to make sure that there's some sort of convention there. And also uniqueness is important, right? Because again, if you're going back to the pets use case, where we try to take stateful applications and run them from within Kubernetes, we need to make sure that each and every machine is unique, and it knows it is unique. And if we have Kubernetes rescheduling that application, that application needs to be rescheduled with the same identity, right? If I'm coming back being rescheduled in another node, I need to make sure that I have the same identity, accessing the same storage, and having the same attributes. Now, the last component is order, because if I'm running a cluster, for example, and if I'm running an application that is originally not intended to be a cloud native application, Order sometimes is very important, right? Because in very common cases, I'm usually starting a master node, and then I have multiple slave nodes or secondary nodes joining that cluster. Now, the first node is very important. It's very important for the other nodes to be able to address that first node or the cluster name directly. So the order is also very important for stateful applications. And luckily, we have Kubernetes taking care for all these components and providing various resources to be able to address these issues. So the first is storage. So let's see how Kubernetes handles storage. So Kubernetes have a lot of built-in providers, in-tree providers, as part of the code base of Kubernetes that allows us to provision and manage and maintain the most common storage providers out there. Obviously, the public clouds already have that pre-integrated. So this makes it very easy to create a volume, a persistent volume on a public cloud, but also if we're looking at a private cloud use case where we install Kubernetes on-premise on our own hardware, we also have drivers for the most common storage hardware for such cases. So let's see at what kind of resources we have at our disposal to configure and to define our use cases. So the first abstract is the notion of volumes. We can define a volume that would be attached to our content, to our pod, and we have a notion of persistent volumes. Now, persistent volumes are basically resources that stay if something happens to our container. If our container fails, the persistent volume stays there. If our containers is being deleted, the persistent volume stays there, so that we can access that from another container after we reschedule our workload. Now, the really cool part is that we also have the availability. We also can access and provision persistent volumes dynamically. So, and we do that by using something that is called persistent volume claim. So we can, when we define our YAML file, I'm assuming all of you have seen, or the ones who have used Kubernetes have seen YAML files for Kubernetes. So as part of the YAML file, we can define a persistent volume claim. And that allows us to dynamically provision a container. So let's go and see at how this works. So we define our YAML, our application in the Kubernetes YAML, which basically builds our pod. Within that pod, we have our container. And within that YAML file, we can define our persistent volume claim. Now, that persistent volume claim is part of the YAML itself. I'm going to show you an example a bit in the next slide. That persistent volume claim is basically claiming some sort of volume from a storage class. Now, what this means is that the storage class basically goes to the provisioner and then provisions our volume for us. And this happens seamlessly in the backend of all the public clouds out there. So when we create when we define and ask our Kubernetes cluster to create a pod with a persistent volume claim, that creates a volume dynamically and provisions the volume dynamically. Later on, it creates the persistent volume and attaches the volume to our containers. So what we've seen here is basically the ability to have these containers portable, and obviously this allows us the self-serve use case, right? When we allow our admin to define his own workload and to provision the persistent volume on demand as the application needs. So here's an example of you wouldn't expect a Kubernetes talk without seeing a YAML. So obviously we are going to review quickly a YAML file. I've seen some laughter back there at the end. Yep. So the way it works, the way it's being defined is that we have the pod. We define the pod as part of the YAML, and we state that we want to have a persistent volume claim. We define the persistent volume claim that we want to use, Underneath that, or in another YAML file, we can define our volume claim, where we define the attributes and the properties that we want to have as part of our storage. Now, here's usually where the magic happens. Here I can define my storage class name. And this is the default example using GCP, using the Kubernetes, using Google Kubernetes Engine. So here I can define that I'm using a storage class name standard, which is a default one provided by a Kubernetes cluster of Google's cloud, and that dynamically provisions a persistent disk run and offered by Kubernetes by GCP. Now, the second part is the ability to have to allow our container, our pods, to have an identity and to have some order to the provisioning of our containers. So we have the notion of stateful sets. Stateful sets are basically a controller similar to a deployment, and it allows us to control and maintain the state of the provisioned pods, and also maintain their identity. So whenever something terrible happens to my container or to my pod, and Kubernetes reschedules that pod on a different node, that new pod gets the same ID, and it gets all the characteristics of the previously provisioned pod. So basically, stateful sets allows us to have stable and unique DNS names. Again, I can have the same name no matter what. I have the same name no matter what happens to the node, and the order of the provisioning is maintained. So what this actually means is that when I scale my cluster, for example, I want to have a 3-node cluster, and I have 3 replica sets per stable set. The order of the provisioning is being maintained. So this means what this means is that I have them numbered when they are provisioned. So let's go quickly over an example. So I have here another YAML example that defines a stateful set. And I have here 2 replicas of this YAML. This is a basic Nginx application, a very simple example. And when I do a get command using kubectl, I can see that I have one stateful set. And that stateful set has 2 pods, and each pod has a name, which is going by a convention of 1 plus n requested pods. So again, 0, 1, 2, 3, and the order is maintained. Now what's really cool is when I scale up the application, the next one is going to be 3, 4, and when I scale down the application or delete the application, it's going to do a delete by a reverse order. So I can anticipate this behavior and act accordingly. Now, what Kubernetes does not provide built-in is the mechanisms to handle these cases. It only takes care of the identity. So if I want to handle, scale up or scale down cases, and I have a persistent application or a stateful application, I need to make sure that my lifecycle operations around the pod actually handle that. So for example, if I have, a join cluster or an operation to remove a node from a cluster, I need to do that manually by myself and handle these cases by myself. But again, Kubernetes does at least allows us to maintain the state and to make sure that when I schedule a container or scale a container, the name persists and remains the same. So the missing piece is that what happens in cases where I scale my persistent set and I want to have a storage per device. So the persistent volume claim I mentioned earlier is basically something that's being created per deployment. But again, if I'm scaling that, I need to make sure that my infrastructure also is capable of handling scale operations and basically provision a new volume every time I scale my environment. Every time I scale my persistent set. So what I can use here, and here's another example of a nice little YAML. So I have a volume claim template. So the volume claim templates is something that allows us to provision new volumes every time I scale up the pod. Sorry, every time I scale up the persistent set, the stateful set, and I get a pod. I get a volume provisioned every time I scale it up. So let's go over a quick demo. So here I have the YAML file that we've seen earlier on. Again, very simple example. I have an Nginx application with a stateful set defined. I have a simple service that just exposes it on port 80. And I don't use a load balancer or anything fancy here. I just use the basic principle, the basic service, headless service. And again, simple image, nothing fancy here. But I also do have here the volume claim template, which means I'm going to have a volume provisioned for every pod as part of this stateful set. And I have a replica of 2. So I'm going to have two nodes here, 2 pods here as part of this stateful set. So let's go over our console. And let's just quickly see if we have Wi-Fi. Okay. In the meantime, we can pray to the God of demos. Obviously, that's going to break, but let's see how it goes. So kubectl get pods. And I can see that at the moment, I shouldn't have anything here. All right, so I don't have any resources here. I have here my nice little YAML definition of my Nginx application. Let's just quickly review that and make sure that's the one. Let's try to increase that. Yes, let's go up. Okay. So again, it's the same file we've seen earlier on. It's the same very basic YAML definition for my service. Again, I have a headless service here, which basically means I don't get an IP managed by a load balancer. And I have a stateful set. I define a replica of 2. So basically, I'm saying I want 2 pods with unique identities, and I want Kubernetes to maintain their identity for me. And I also have this notion here defined for volume claim templates, which means I want a volume per pod. So that's a very basic template. Let's try to run it. kubectl apply. I want to run this file, so I'm going to do web.yaml. All right. It didn't break. I'm happy. So now I can actually see what's happening here. kubectl get. For the ones who don't know the shortcuts, I'm going to use the long ones. So yeah, again, in the meantime, it should have created a stateful set. All right, no, I want to have a typo. All right, so I have a stateful set, web. I want 2 containers and actually have 2. I want 2 pods and actually have 2 pods for this stateful set. If you're going to see what's happening, how many pods we have now. So I have 2 pods. One is called Web 0, one is called Web 1. So I see Kubernetes maintains that convention, and if I'm going to kill a pod, it's going to create it. Let's try to do that. kubectl delete. Let's be brutal to this guy. Yep. Thank you. Okay, so I've deleted that pod. Let's do get again. And I see here Kubernetes actually maintains that. and I see it's creating this pod for me. And it also in the background also attaches the volume it created for it. So let's just quickly see the volume. Get persistent volumes, and I see I have 2 persistent volumes here. I have unique IDs for them, and I see that they are bound. They are attached to my containers. And if I want, I can actually go into detail and do. And do a describe command and see what did I miss? Yeah, God's of a demo. Never mind. So, but basically, I get my pods here, and I get my persistent volume claims here, and I can see that they are being attached. And also, if we really want to look at a nice fancy UI, we also have in the background here Google Kubernetes engine running this for me, and I see also these two volume claims are being created and bound to my containers. So to summarize, what it takes to run a stateful application in Kubernetes, you need to make sure that you got a storage that is persistent. You need to make sure that you have the name of the storage persistent, and you need to use stateful sets. You should use stateful sets to make sure you have these statically assigned, and Kubernetes would maintain their order and identity. But Kubernetes does not take care of the application itself. I've heard this several times already in this conference. Obviously, this is one of the things that Kubernetes does not yet provide enough rich enough tool sets, is to make sure that the application itself knows how to handle these identities, and knows how to scale up or down based on the application itself, based on these identities. And that's pretty much what I have. Thank you.